Okay, so last time we talked about how the elements are formed. And the whole idea behind this is that we're trying to build up the story for how the universe formed and how you make a habitable planet. And the Big Bang, of course, is everywhere. And then the elements are being made everywhere. And so this is making elements in certain proportions that are going to be fairly similar throughout the universe. And the elements that are made are going to be the ones that go into making planets and then go into making life. And so why are we made up of carbon, hydrogen, and oxygen mostly? And why is the Earth made up of silica, magnesium, magnesium and iron mostly, and oxygen? Why are those elements important? And how is it? And if they're important on Earth, is there some kind of unique thing? Or are those going to be the important elements everywhere? So we learned that helium and hydrogen formed in the Big Bang. That's it. There's expansion, everything's cooling down, so nuclear fusion can't take place. And then you form stars, and in stars you form elements by fusion, and some neutrons are absorbed in the stars. And then you have supernova, which sends big blasts of electrons going out to create the heavier elements beyond iron 56. And that leads to this important diagram. So I want you to know what is the chart of the nuclides. It has the number of neutrons on the x-axis and the number of protons on the y-axis. And it has those colored little things, which are all the stable isotopes of all the elements. And it has these red things, which are all the radioactive isotopes of all the elements. And the red things all undergo radioactive decay and end up in this central band. The ones down here migrate up that way to the band. The ones up here migrate down that way to the band. Because when you undergo radioactive decay, you change the element identity. And if you look, we're going to zoom in on the chart of the nuclides now. And so here we're looking at it in more detail. So here again, number of neutrons, number of protons. So we've blown it up. So we only have 20 neutrons here and around 20 neutrons on the vertical axis. And then we have these open boxes. These are all the stable isotopes of all the elements. And we have a few black boxes. Those are radioactive elements that have long enough half-lives that they're still around somewhere in the solar system. And you'll notice that when you take an element like, let's see, an element that's familiar to you, titanium here, you can see there are 4 different boxes, and those 4 different boxes are the 4 isotopes of titanium. All titanium has 22 protons, but it can have either 24 neutrons or 25 or 26 or 27 or 28. So there are 5 different isotopes of titanium. If you look at its neighbor, scandium, down here, you may never have even heard of scandium. It only has 1. And you go up here and there's chromium. It's got 4 isotopes. Manganese has 1. Iron has 4 isotopes. Cobalt has 1. There's a pattern there. Can you tell what it is? It's the evens. The elements with even numbers of protons are much more abundant. And if you have even numbers of protons and even numbers of neutrons, you're particularly abundant. And so you'll see here you're even, 5 isotopes, odd, 1. Even, 7 isotopes, odd, none. Technetium is radioactive. Even, 7 isotopes, odd, 1. Even, 6 isotopes, odd, 1. And because you have many, many more isotopes of these even-numbered elements, you have much more of them. And so the even-numbered elements are much more abundant than the odd-numbered elements because God likes pairs. Okay, he just does. Like on Noah's Ark. They went in pairs. And there's another way that this works that I've drawn this blue arrow here, and that's along an isobar. In this case, the isobar where the total number of neutrons plus protons is 96. And you see you have a box here, that's 1 element. You have a box here, that's of a second element. You have a box here of a third element. If you go to 95, there's only 1. If you go to 94, there's 2. If you go to 93, there's 1. If you go to 92, there's 2. If you go to 91, there's 1. So Evens win all ways you look at this diagram, and for that reason, the even-numbered elements are much more abundant than the odd-numbered elements. And it turns out that multiples of 4 are even more preferred, and those are called the alpha particle nuclides, because an alpha particle is a helium atom with 2 protons and 2 neutrons, so we call that an alpha particle. It's the nucleus of a helium atom. And this is the abundance of all the elements in the sun, and this is the sum of neutrons and protons. And you can see that you have carbon up here, which is 12, and then it's odd. And then you have oxygen, which is 16, 4 greater, that's really abundant. And then you go down to things like fluorine. And then you have neon, a noble gas, and magnesium and silicon and sulfur and argon and calcium, all of those elements you've heard of. And if you look at oxygen compared to its neighbors, it's up here above 10 to the 7th, and its neighbors are down here at 10 to the 4th. It's 1,000 times more abundant, because it's made up of this particularly stable assortment of particles where you have 2 protons and 2 neutrons. And so all of these guys are inevitably going to become the most important elements, except neon here and argon are both noble gases, so they're non-reactive, so they're not going to be that important. But all the other things that actually make molecules become very important. And then you have a peak out here at iron. That's because you're making things by nuclear fusion, and ultimately you end up fusing 2 silicon atoms here. 2 times 28 is 56. And that comes up to 56, then you can't do fusion anymore. So as long as you're making these guys, you make it, you add a helium atom, you make another one, you add a helium atom, you make another one, you make a helium atom. There's an assembly line, and you go to one portion of the assembly line, and then you move on to the next portion of the assembly line, then you move on to the next portion, and you get to the end of the assembly line, and it's iron, and it can't go any further. So there's a pile-up. And so you get the alpha particle nuclides down here, which are superabundant, and then you have the pile-up at iron, and after that the abundances go way, way down, because those elements are only made during supernova explosions, and sometimes in the interiors of very large stars, but then get blown apart as supernovas. So when we look at all the elements now, starting from hydrogen, we have an overwhelming abundance of hydrogen in the universe. It's 1,000 times more abundant than everything else. And then except for helium. And then you have helium, which is about 10% as much as hydrogen. And then you have the alpha particle nuclides with the buildup of iron and then the decay after that. So these are the Big Bang elements, hydrogen and helium, and then very small amounts of lithium, beryllium, and boron at this mass trap at mass 5. Then you have nuclear fusion in stars, which makes these, and particularly the alpha particle nuclides in abundance, with a pile-up at iron. And then you get a big decrease in the numbers of the elements as you go to heavier and heavier elements. And this sawtooth thing, up, down, up, down, up, down, up, down, is even, odd, even, odd, even, odd, even, odd, even, odd. And up here, you have these multiples of 4, which are particularly abundant. But you also see the strong even-odd effect with a particular preference when you're multiplying by 4. That's going to be true throughout the universe because it's the basic laws of nucleosynthesis in stars. So that's going to control the abundance of the elements in all the solar systems of the universe. So this is then what I want you to remember, that the elements are made in really 3 different ways. During the Big Bang, you make hydrogen and helium and little tiny bits of the next 3 elements, which are lithium, beryllium, and boron. And then, once you get a star that's big enough, you make the alpha particle nuclides. That's things like carbon, oxygen, magnesium, and other elements, up to iron 56. All of that is happening by nuclear fusion in stars. And elements heavier than iron 56 formed by neutron addition in stellar interiors. We call that the S process. And during supernova explosions, we call that the R process. S and R sound like there's some technical jargon, okay, but S stands for slow and R stands for rapid. So you make them slowly as they cook in the stars, and you make them rapidly as the stars explode. And that makes all the elements heavier than iron 56. And ultimately, as you add more and more neutrons to the elements get so big that there's so many protons in them that they can't stay together anymore, and they fall apart. And that's called nuclear fission. So you can't make elements heavier than uranium. Uranium is slowly falling apart. That's why we can make nuclear power plants. Once you get heavier than uranium, they fall apart much more rapidly. And that gives you this overall distribution. It's nice if you don't know the details of this diagram, but if you can sketch it, you've got hydrogen and helium way up here. You've got these low mass elements down here. You have the alpha particle nuclides out to iron, and then you have this long tail going down out to the heavier elements, and you end up here at uranium because above that the elements fall apart. Okay? So what are we left with? We have lots of hydrogen. Well, that's great. That allows long-lived stars like the sun, which burns hydrogen. So we're left with the raw materials to make gazillions of stars all over the universe. And we're left with lots of these elements, hydrogen, of course, and then carbon, oxygen, magnesium, sulfur, calcium, and iron. And these become the important elements for the whole rest of our story. And the carbon, hydrogen, and oxygen, those are going to make life. And the oxygen, magnesium, calcium, iron, and sulfur, those are going to make planets. And you're going to have important molecules on planets that are like H2O, water. Oh, why is water so important? Because those elements are two of the most abundant elements made during nucleosynthesis. And you're going to have CO2. Oh, look at that, CO2. And you have us made up primarily of carbon, hydrogen, and oxygen. Why are we made up like that? Is life likely to be made up of something else in the universe? No. Because the universe makes these really important elements in these superabundant ways, and that's what's going to be used throughout the universe through on. So where we're going now is what happens to these remnants of supernova explosions cool down. We have all these elements. And those elements don't stay separated anymore. They form molecules. And so we're going to see which molecules they form and what the laws are of the molecules that they form. And then this material is going to exist as dust, as ice, as gas. And from that materials, then, we're going to make a solar system like ours. We're going to make the Earth. And we're going to add all the necessary molecules that are needed in order to make life. And they're going to be made up of these superabundant elements. We can see this happening in our own galaxy today in places like this. This is the Orion Nebula in the belt of Orion. And in this Orion Nebula, you can see stars forming. You can see solar systems forming. You can see the molecules forming that are going to make up the planets and life. You can see the molecules coagulating around stars to make planets. You can see this whole process. This is like a stellar nursery where you're making new stars and making new solar systems and making elements as the supernovas go off, and they're fertilizing this cloud, and then those fertilized elements are being used to make solar systems, and then the cloud ultimately busts apart, and you end up with solar systems like ours skirting around the Milky Way galaxy. So new solar systems are being formed today in places like that within our galaxy, and of course in every galaxy of the universe. Okay, so I like to talk about different levels of reality, and it's it's related to a bigger idea, which is that there are different dimensionalities of reality in the world. See that the wire has worked its way from the top all the way through the ice, and now it's right there suspended in the middle of the ice. And pretty soon it's going to drop through, and I'll be able to pick up this ice cube. We'll see why that is, hopefully by the end of the lecture. And this is dry ice over here, and the wire's not going through. So How come the wire doesn't go through the dry ice and does go through this ice? So we'll learn about that in a bit. Okay, so you're all familiar, or maybe you're familiar of a one-dimensional world along a line. And in that one-dimensional world, you have one person here and you have another person there, and you can never change places. To change places, you'd have to go around this way or go up over that. You'd have to have another dimension. So it's impossible. The sequence that's on this one-dimensional world, 1, 2, 3, 4, is always there. You can compress them, you can stretch them. There's certain things you can do, but you're limited. There's just nothing you can do about it. That's the law. It's absolutely impossible to change that sequence. But of course, if you go to a two-dimensional world, and you have 1, 2, 3, and 4, they can move around. You can change the sequence, they can change places repeatedly. What's possible in this world is completely impossible in that world. And in the same way, you're restricted here in this two-dimensional world because you don't have 3 dimensions. And when you have 3 dimensions, then you can move in space, and that creates things that are absolutely impossible in the two-dimensional world. And when you add the 4th dimension of time, you also create other laws that are completely different. So stars and planets are like that. Stars are one level of reality where you have temperatures of millions of degrees, electrons are not bound to nuclei, and one element is transformed into another element all the time. It's normal, everyday stuff. When you go down to planets, you have lower temperatures of thousands of degrees, electrons are bound to the nucleus, and all the interactions take place between electron clouds, not between nuclei, and the electron sharing creates molecules, and we have a whole different series of laws that apply in the planetary world that are completely violated by the stellar world. It's a completely different level, it's a different dimension of reality. And the black hole world is going to be a whole different dimension of reality relative to the world that we see in stars. When you get to the fundamental particles that make up things like protons and neutrons, there's a whole different set of laws that apply there that are absolutely impossible within the stellar world. And I think this is a reason why we're so afraid of nuclear power. And it's not just because we can make bombs with it, but it's a different world. It's a whole different level of reality, radioactivity. Did you know all of you have radioactive elements in you right now? Carbon-14 is in you, decaying, emitting radiation into your body. Scary, okay? But also they're coal power plants, and the coal power plants are, 100 times more dangerous than nuclear power plants. The health hazards that they provide to the general population are just extreme, especially in places where you don't have good pollution controls. And so we have this 2 levels of reality, and I think that makes us afraid of things that objectively we shouldn't be afraid of. Nuclear power is incredibly safe. So in the past lectures and the beginning of this one, we've been talking about the stellar reality, where all the elements are made. Transforming one element to another is normal. It takes place because the nuclei interact. And from now on, we're not going to be talking about that anymore until we talk about radioactive dating, which is sort of a remnant of that in our world. Instead, we're down to the world where the atoms become surrounded by electron clouds, and everything that happens depends on how these electron shells around the atom, around the nucleus, interact with one another. And so you're going to form molecules because the electron shells interact. Atoms will try to fill their electron shell structures, which minimizes their energy. They want to have charge balance, and they also have to fit together in terms of size. There are all kinds of ways that they need to adjust to one another. And I can't, as I've said before, I can't show you the nucleus on this diagram because it would be too small for you to see. But the atom is this big cloud around the little tiny nucleus, and it's going to bump into another cloud, which is an adjoining atom, and all the interactions take place between those clouds. The number of electrons in the cloud is controlled by the number of protons in the nucleus, but the interactions occur among the clouds themselves. So for elements, the number of electrons is controlled by the number of protons in the nucleus because the electrons are negatively charged, the protons are positively charged. The electrons arrange themselves in shells around the nucleus. All of the chemical interactions depend on the interactions between these relatively huge electron shells. And the atoms can share and donate, receive, loan their electrons. And we call this change in the number of electrons the valence state of the atom. If you lose an electron, that's losing a negative charge. You get a cation, which is a positively charged ion. If you gain an electron, which is a negative charge, you have an extra negative charge, so you have a negative ion, which is called an anion. And the chart of the nuclides was the chart that we used for understanding what happens in stars, and the periodic table of the elements is the table that we use to understand what's happening with atoms. And these things reflect the characteristic of the outer shell, and this on the inside reflects what's happening with the inner shells when you're making the atom. And this, once you learn to read this diagram, then you realize that it's kind of a symbol of atomic structure. Now, there are other ways of presenting it. So, when I was a kid, my father had a friend who thought that making the periodic table like this didn't make any sense. He should make another kind of periodic table. So he made this one. Pretty cool, huh? So you have the inner shell. You have 2 electrons. That's hydrogen and helium. And then you have your next shell where you have 8. That makes all these elements. And you can go around on this line as you go up in atomic number. And then when you get out here, you start adding elements, adding electrons to the inner shells. That makes these transition metals. So you start over here with, after calcium, you go into an inner shell with scandium, titanium, vanadium, chromium. Well, that's just like this. After calcium out here, you're going to an inner shell. And so this actually presents much more accurately what the electrons look like, or where they're situated in the electron cloud. Of course, the nucleus should be a little tiny thing. And these outer shells become bigger and bigger. So when I was 8 or 9 years old, my father put this up on the wall of my room so I would go to bed at night looking at this and pondering on the structure of the atom. Can you imagine anything so nerdy? But I still have it. And I've always thought it was a better way of representing the periodic table. But if you look at this in the right way, you can see it in the same way, that these inner bounds are where you're filling in inner electrons, and these outer ones are what's happening on the outer shells, the ones that have the brighter colors. What are the numbers in each box? Because, I've been talking about iron 56 that we write like this. But if you look at iron up here, it's got a 26. What's going on? Yeah. It's just the number of protons. So if you were to count the boxes, hydrogen is 1, helium is 2, lithium is 3, beryllium is 4. You just count them up going from left to right. You get to 26 at iron. So iron 56 has 26 protons and 30 neutrons. And so when you write the superscript right next to the element, that's the total number of protons plus neutrons. But on the periodic table, it kind of looks like it's a superscript, but it's farther away and refers to the total number of protons. Okay, so in the periodic table, the horizontal rows reflect the number of electron shells. So hydrogen and helium, that's the first shell. You see it there. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. That's the second shell. It's this one. Then you go out to the third shell, and then you start filling in. So And each additional shell holds larger number of electrons, so you had only 2 here and 8 there, and you get more and more as you go out further because you're farther and far from the atom and from the nucleus, and you can fit more in. And elements with the same number of electrons in their external shell are lined along these vertical lines and have similar chemical behavior: hydrogen, lithium, sodium, and so on. Okay, so now we need to take all these atoms, and they're mostly unhappy. They're unhappy because they're incomplete. Their electron shells are partially empty, and they become happy when their electron shells become filled. And so you have a group of happy elements called the noble gases. They're out here. They have their electron shells filled. That means they're totally non-reactive. And that means they were the last elements to be discovered because they didn't react with anything. And they just exist as gases. You're breathing them in all the time, but they don't have any biological effect on you because they have no electron shells to interact with, so they don't interact with other elements. So if you want to be invisible, be non-reactive. So you walk into a room and you want to be you go in, "Hi everybody, here I am." You talk and you're reactive, everybody chats with you, they know you're there. You go into a room and you interact with no one. They don't even know you were at the party. You're completely invisible. So if you ever want to be invisible, be like a noble gas. All right, so the molecules are stable when the outermost shell is full. And noble gases already have a full shell. So elements with only 1 or 2 electrons in their outer shell can easily get rid of their electron. They're chemically very reactive. And elements that are more closely aligned, almost full, can be less reactive or give off less energy when they react. So let's see how that works. We can have oxygen and hydrogen. Hydrogen has only 1 electron in its outer shell. It would like to have 2. And oxygen is missing 2 electrons in its outer shell. So hydrogen would be happy to have 2 electrons, and oxygen would be happy to receive 2 electrons. And so by combining the two, the oxygen gets a completed shell and the hydrogen gets a completed shell, and you have a happy molecule. So they're going to combine with each other in ways that make their electron shells satisfied. But you can see when you look at this that they also have different sizes. And so you get the hydrogens on one side, that they're positively charged, and the oxygen on the other side, that tends to be negatively charged. So you get this sort of little magnet. And that's because the hydrogen atoms are so tiny. You can also fill shells by sharing electrons. So this is the diamond structure. So you have carbon, which is missing 4 electrons. And so it can give or receive, and by the carbon atoms joining together, they can make completed electron shells for each other, and that makes a particularly hard and stable element, a stable structure, which is the reason why diamond is the hardest structure known to man. Or you can combine positively and negatively charged things, like chlorine is missing an electron and would like to receive one, and sodium has an extra electron and would like to donate one. So the sodium gives its electron to the chlorine. The chlorine receives an electron. It now has more negative charges. It fluffs up. And the sodium loses an electron, so its nucleus has more power to pull in because there's a smaller number of electrons, so the sodium contracts. So you get little sodium atoms and big chlorine atoms, and they join together to make that nice cubic structure. So when you go back and you look at your salt shaker at lunch or dinner, and if you look carefully at the salt shaker, you'll see that it's made up of little tiny cubes. And those little tiny cubes are not here. Well, this is I'll bring in a better halite crystal next time. But this is a if you look at this thing right here, you can see that big cube. And when you best it up, you'll make little tiny cubes. When you look at your salt in your salt shaker, you'll see it's made up of little tiny dice, little tiny cubic things. Okay, so you have to fit them together in terms of their size as well as their charge. So you have to adjust the electron shells to fit, and you also have to make them fit together. And when you have some atoms are big and some atoms are small, and so how are you actually going to have those all fit together geometrically? And generally, anions with negative charges are big and the cations are small. And so the overall structure of a mineral is determined how those big ions hang together. So if you have big anions like this, you can fit them together in triplets, and then you can fit a little tiny cation in the middle. Or you could fit them together like this, and now you've got a bigger hole in the middle. So this could only take a very small cation, and this one could take a bigger cation. Or you can stack them on top of one another, and you can create an even bigger cavity in the middle. And so it's going to organize itself so there's space for the different ions that have different sizes. And so there's the triangular coordination, which can only take a little tiny cation. And then tetrahedral coordination is when you have 3 balls on the bottom and 1 ball on the top, like a pyramid. And octahedral coordination is when you have 4 in the middle and 1 on the top and 1 on the bottom. And cubic coordination is when you have 2 4s stacked one on top of the other. And each one of those creates a cavity of a different size. So that's going to control which other element can fit in there. It's simple geometry. And one of the most important geometric structures is the silicon tetrahedron. Here it's exploded apart. Here it's not exploded apart. It's a pyramid. And you have a little silicon atom in the middle, and you have 4 oxygens surrounding it. And that makes this unit SiO4, and that forms the silicates, which are the most important mineral group on all the rocks that you see on Earth. Why? Because they're made up of silicon and oxygen, 2 of the most abundant elements made during nucleosynthesis. So you've got to have the electron shells fit together properly. You have to have the geometry work so that they fit together in terms of size. And they have to be charge balanced so they don't end up being positively or negatively charged. So you can write the chemical formula for the various minerals in terms of integer numbers of different atoms, and those form together to form neutrally charged species. Calcium carbonate is limestone, marble. SiO2 is quartz. That's another mineral that's the most important mineral in Earth's interior, called olivine. Okay. Then the next thing you do is you have to be able to build things of macroscopic size. So here we have a sodium ion and a chlorine atom, and they are making these cubes. And you can see on the top there's room for another layer to be formed that's exactly the same as the layer underneath it. So you're able to build up the layers one after the other, and you're able to make something big. So when you look at a halite crystal that is a big size like this one, this is actually a reflection of the details of this atomic structure. So the large mineral is actually making the invisible atomic world visible to the eye, because everything is built up exactly symmetrically. If you didn't do that, you could never make macroscopic things. You could never make big things. They'd never stick together. So if you want to make big things like minerals, you've got all the minerals of the world, like you're going to be making a mica. This is a single mineral. And if you want to make something big like this, you have to be able to have it build up infinitely. This could go as big as you want. They used to use this for windows in Moscow. That's why it's called muscovite, because these layers were very good thermal insulators. Okay, So how do you build things up in infinite layers? The only way you can do it is if it's symmetrical. You face this problem whenever you're making a floor or a bathroom wall. You don't want any holes in it. So you have to build a structure that would... okay, so what's happened here is this is almost fallen through. Okay, so if you look at this, you see there's just a little bit of the wire left coming out. And if I were able to hold this for you for another 5 or 10 minutes, the whole wire would pass through. And so the wire has passed through the ice cube, but the ice cube is still there. Amazing, isn't it? It's like magic. We'll get to that in a minute. Okay, so if you want to tile a floor, you can do it like this. You can do it other ways too. You can make things really pretty, like that. And if you look at any floor, and I'm going to ask you to look at floors between now and Thursday, you will see that it has a certain symmetry associated with it. And one of the ways we describe symmetry is by talking about symmetry axes. And it turns out the only symmetry axes that are available in the universe are 2, 3, 4, and 6. So a symmetry axis means when you have a pattern like this one, and you stick a point in it, and you imagine a pole coming out from that point, and the pole is coming out like this, and you rotate it, and it looks exactly the same depending on how far you rotate it. So what is this symmetry axis for this pattern that I've drawn here? If I rotate, how much would I have to rotate it for it to look exactly the same if I rotated it around that point? Well, if I did 90, it would look like this. Because it's a little bit longer this way than it is that way. So it has to be 180. If you rotated this all the way around, then you wouldn't be able to tell whether I'd rotated it or not. If you have perfect squares, then it's 90. And so we call this a two-fold rotation axis. You can rotate it twice. We call this a four-fold rotation axis. You can rotate it 4 times and get exactly the same thing. What's this? Does it have rotation axes? And what fold is it? And where is it? That's from the Alhambra in Spain. In the Alhambra in Spain, they put all possible classes of symmetry on the tiles of the walls. So 1,000 years ago, they knew all the laws of symmetry, and they created the tiles to express all of them. This is one of them. Anybody? Yeah. Where?
The Black Star one, you rotated it 90 degrees.
This one?
The one next to it.
This one.
Yeah.
Yeah, so that has a fourfold around it. So this thing would rotate up to there, this thing rotates to there, this thing rotates down to here. That's a fourfold axis. What's here? Yes, it would be a twofold if you ignored the colors, right? Ignored the colors. There's also a mirror plane if you ignore the colors. So there's a mirror plane down here. So you're mirrored across that way. You're also mirrored across this way. Are you mirrored across this way? No, yes? Yes. So it's got a lot of symmetry elements. It's got a four-fold axis, it's got a two-fold axis, it's got three different mirror planes. So that's a really cool and complex example of symmetry. This is your common Harvard sidewalk. Whenever you see a pattern that's regular and continuous, it has symmetry. It can't be constructed otherwise. So what's the symmetry element here? The symmetry elements you can look for are two-fold axes, three-fold axes, four-fold axes, six-fold axes, and mirror planes. Not so easy, huh? Yeah. You're a ROF, is it? Yeah. Twofold. Where? Where? There. Yeah. So the shape is this one. And if you rotate a two-fold axis around this, that brick rotates over to this brick, and this brick rotates over to that brick. It's got very limited symmetry. You might want to say, no, wait, doesn't it have a mirror plane here? No. No mirrors. No four folds. It just has two-fold symmetry. How about this one? You have to carefully look at the shapes of the tiles. Yeah, who's going to be brave? Okay. Does it have a threefold? No. Doesn't have a threefold. Does it have a fourfold? Where? Does it have a fourfold here? Looks like it. This rotates here, that rotates there. No, because this long piece would rotate down this way. It's not replicated. So it has a fourfold axis here because this one rotates to this, and this one rotates to that, and this one rotates to that. And it has twofold axes here because this goes back. It also has a mirror plane here. It has a mirror plane there. Does it have a mirror plane like this? No. How about this one? Where's the 6? So here. You have threefold here. This thing rotates to there. This thing rotates to there. You have mirror planes here. You have mirror planes there. You have mirror planes there. So you can see all these different ingredients, and if you go into Excel or something like that, you can take you can take things like, say, polygons. So this is a 5-sided polygon, and you could try to make a repeating pattern with polygons, and then you could say, aha! They said there was no 5-fold symmetry, but I've taken a polygon and I've made one. What's the symmetry element of that pattern, apart from the little slip-ups that I made in putting it together? Like, you've got a twofold axis here. You've got a mirror plane going through there. You have a mirror plane going through here. And those 5-fold things, you don't have 5-fold rotation, even though you've got pentagons in the pattern. There's no 5-fold rotation axis. There's no 5-fold rotation axis anywhere in the universe. Nowhere. You can't make it. You can only make 2, 3, 4, 6 in mirror planes. And that's going to govern the minerals that are formed, because only macroscopic things can form minerals, and only when you have repeated patterns can you make macroscopic things. And you can only have repeated patterns if you have symmetry, and if you have symmetry, you only have these ingredients that can be combined in various ways to make the symmetry elements. So what I'd like you to do is, between now and Thursday, you walk around campus, totally aware, and now you look around and you see, oh, I'm surrounded by symmetry elements. Every bathroom you go into, every floor you look at, every sidewalk you see, provided it's well constructed, every patio that's not like a random mosaic, everything you see that's continuous is made up of symmetry elements. So you take a picture of it and you send it to me. Now you don't do something like this. Take a picture of a lamppost, okay, which has a light bulb in the middle of it. And you say that it's symmetrical, see? Right down the middle, it has a mirror plane. No, you have to find patterns that can be infinitely repeated. Or you can make up your own pattern and infinitely repeat it and send it in. And then we'll have a little show and tell on Thursday of the beautiful symmetry that you found all around you as you walk through the world. All right, so to see where we've come from, then we have stars that are formed in interstellar clouds. The big stars have short lifetimes. They make all the heavy elements and distribute all the elements through this stellar nursery. And later generations of small stars have those elements available to them to make hydrogen-based long-lived stars with planets around them that can be stable solar systems. The element identity is controlled by the number of protons in the nucleus, because that controls the number of electrons in the cloud, and the number of the electrons in the cloud controls how the elements interact with one another. And because most outer shells are incomplete, most atoms combine to form molecules, and they bond together in several different ways. But they have to follow certain rules. They have to have electron shell compatibility, and they have to be charge balanced. They have to fit together in terms of size, and they have to make symmetrical elements that can make macroscopic objects. And when you satisfy all those things, you make the minerals. And the minerals then become essential for what comes next, because they are going to be the materials that make up all the planets and ultimately are there to be able to support the creation of life. So planets are entirely made up of minerals. And the most important minerals make use of these most abundant elements that are made during nucleosynthesis. And you have inorganic molecules, and those are minerals. They have no carbon-hydrogen bonds, and that's the minerals. And you have organic molecules that have carbon-hydrogen bonds. They're going to make life. And the minerals have this definition. They're solid. They occur naturally. If some chemist working for a company makes a new substance that can be a solid, it's not a mineral if it's not found in nature. They're inorganic. They have homogeneous physical properties. They're symmetrical, and they have a chemical composition that can be written as a formula. And all of that defines what the mineral is, and that's what they're made of. So we have some nice minerals up here. We have halite. We have pyrite, which is fool's gold. Pass that around, it's so pretty. That's iron sulfide. So made up of two of these most abundant elements. You have muscovite, which is another silicate. It's made up of layers. So when that's the third one down here on the bottom. You're combining these silica tetrahedra into hexagonal things that form long, flat sheets. And those long, flat sheets are stacked together so they look like this. So you have this long, flat sheet like that, hexagonal looking down this way, but flat going the other way. So when you look at this, these are all the flat sheets of that structure. That's why you get a mica that can be flaked like that. That's all the flat one. And if you get a well-formed crystal of this muscovite, so You can see that's why it would be used as a window, because you can see through it when it gets thin, and it's also a great thermal insulator. And here, you can't see the whole hexagon, but you can see two sides of the hexagon. So you're looking vertically down at it, just like you'd be looking vertically down at this sheet. That made this angle, and then the flat sheets made these flat angles. So all these minerals then have something that we call physical properties. And the physical properties are things like how hard they are, how dense they are, when they melt, when they turn into a gas. And we can describe those in things like phase diagrams like this one. So I'll have to go over this next time. So this is water. And we have the pressure up there and the temperature on the horizontal axis. And we live at 1 bar, which is the 1 on that axis. So when you increase the temperature, you go directly from solid to liquid. And that happens at 0 degrees centigrade. But if you change the pressure, if you go up in the atmosphere where the pressure is lower, or you go down into the earth where the pressure is higher, the melting temperature of the water changes. So what happened here was we had a block of ice which has a certain melting temperature, and I put the wire on it with weight, and that increased the pressure. So we were here at 1 atmosphere, right there at the boundary between solid and liquid, and I increased the pressure by having the wire pressing on the ice. So what happens? It presses on the ice, it goes into the liquid field. But once the wire has passed, the pressure drops down again, and so it freezes. So where the wire puts pressure on the ice melts, and after the wire has passed, the ice refreezes, and so the wire can pass directly through the ice cube and fall through at the end, leaving the ice cube intact. Because of the pressure change that's happened, you're continually melting where you have the wire hitting, and it's freezing afterwards because of the ice on both sides. But if you look at this kind of pressure-temperature diagram for carbon dioxide, you ordinarily at room temperature we're down here, and so it doesn't melt, it goes directly from solid to gas. And when you increase the pressure, it just stays solid. So the wire on the dry ice over here never goes through because it never melts it, never causes any movement at all. Whereas the wire going through the ice changed the pressure. So the different ways these substances behave strongly influence how they're going to be interacting on the Earth. For example, when you have an ice sheet and a glacier, and the glacier is sitting on the bottom of rock and it's pressing on the bottom of the rock, it's increasing the pressure. What does that do? That lowers the melting temperature. So it can lubricate the ice. Or the fact that ice floats means that when you form ice in the ocean, it rises up to the surface, and ultimately the cold water comes up to the top. And so the ocean circulates. Whereas if the ice sank, then the ice would sink down to the bottom, it would stay cold, and you wouldn't have ocean circulation. So the physical properties of these materials are going to control very much how they're actually going to be behaving in terms of all the Earth processes.